and then read this wonderful announcement again. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are 2 different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. Okay, so now we're going to take a look at section 9.3, which is simplifying and combining radical expressions. Okay, so consider this. The square root of 9 is 3. The square root of 3 squared is 3. The square root of 25 is 5. The square root of 5 squared is 5. So what's the square root of 17 squared? Anybody?
$17.
Bingo! You got it. The rest of you, do you get it? But you're just the quiet, silent, or strong, silent type. Okay. So what's going on here is well, in fact, look at it this way. If we take the square root of 17 squared and we wrote that in exponential form, wouldn't that be 17 to the 2/2 power, because there's an implied 2 there? But isn't that just 17 to the 1 power, or 17? So if the index matches the exponent inside, they reduce down to 1/1. So you've got the base raised to the 1 power, or just the base. Okay. Now, what about the cube root of 8 cubed? Well, that would be 8, right? Because the index and the exponent would reduce things down. Okay. Now, we're going to do something called simplifying a radical. And you need to understand that back in the day, long ago, when they didn't have fancy calculators that could do things very quickly, and this was all done by hand, this process of simplifying the radical made it easier to deal with. I say that because we're going to look at some problems where the answer is going to look more complicated than the question, and we're going to say, how is that simplifying it? But the idea of simplifying a radical means getting everything out from under the radical that you possibly can. Okay, let me give you an example. Let's take the square root of 50. Okay. How could I simplify that? Well, there's a rule, and this goes back to section 5.2 again. Okay, and let's take a look at that rule. The rule says this: if we have a product raised to a power, we attach that power to each factor. We looked at this a little while ago, right? So that means that the quantity AB to the nth power could be written as A to the n times B to the n. Okay, what if I had AB to the 1/n power? Wouldn't that be A to the 1/n times B to the 1/n power? Okay, it's just using the same rule. I've got a product raised to an outside power, so I attach that power to each factor inside. Okay, but let's take this expression and let's write it in radical notation. What would it look like? We'd have the nth root of AB equals the nth root of A times the nth root of B. So what that says is if I have a radicand, that's the quantity inside the radical, if I can break it up into separate factors, I can deal with each one of those factors separately. So I can take the nth root of A times the nth root of B. Okay, now why would I want to do that? Well, let's go back to this problem 50, the square root of 50. 50 is not a perfect square, but if I took 50 and wrote it as 25 times 2, I could then rewrite this like this, and then I could split it up like that. Why would I want to do that? Well, since my index is that implied 2, by finding a factor that is a perfect square, I can take the square root of 25, which is a 5, outside of the radical, and then the square root of 2 remains inside. So what do I get? The square root of 50 equals 5 square roots of 2. Now, as I said, this does not look simpler than that, but by definition, it's simplified in that we've taken out all the perfect square factors that we can. Okay, so simplifying this, you would get that. All right, let's take a look at another example. The square root of 28. Well, let's see. So what I'm trying to think of is, what is the largest perfect square factor of 28? Okay, so what times what is 28, where we've got a perfect square? And maybe you see that it's a 4 and maybe you don't. Let's say you don't, okay? So let's do this. Let's break this thing down into prime factors. Oh, there's a perfect square, isn't it? 2 squared or 4. So I'm going to rewrite 28 as the square root of 2 squared times 7. And I could also just write 4 times 7. But that's the square root of 2 squared times the square root of 7. And what is the square root of 2 squared? It's a 2 on the outside because we're unsquaring the square. So I get 2 square roots of 7. So the square root of 28 simplifies down to 2 square roots of 7. So I've reduced the amount inside the radical. We okay with this? All right. How about this one? 9 square roots of 54. So my index is a 2, so I'm still looking for perfect square factors. Let's see, 54 is 9 times 6. Oh, 9 is a perfect square. So I'm going to rewrite this as 9 times the square root of 9 times 6, which is 9 times the square root of 9 times the square root of 6. What is the square root of 9? That's 3. So I've got 9 times 3 times the square root of 6, or 27 square roots of 6. 6 breaks down to 2 times 3, but there's no perfect square factors there other than a 1, and that doesn't get us anywhere. How about this one? The cube root of 40. So now my index is a 3, so I'm looking for perfect cube factors. Well, 40 is 8 times 5, and 8 is 2 times 2 times 2. It's a perfect cube. So this is the cube root of 8 times 5, which is the cube root of 8 times the cube root of 5. The cube root of 8 is 2, so I get 2 cube roots of 5 as my final simplified answer. So we're trying to match the index with the exponents inside. Okay, so in fact here, let's go further with this. So this would be 2 cubed times 8. So I could have written that the cube root of 2 cubed times 5. So then the cube root of 2 cubed times the cube root of 5. The cube root of 2 cubed is 2 outside, because the index and the exponent reduce down to 1 over 1. 2 to the 1 power is just 2. Okay. All right. Now, let's see here. How about the 4th root of 32? So I'm looking for something raised to the 4th power. 32 is 2 times 16, which is 2 times 2 times 8, which is 2 times 2 times 2 times 4, which is 2 times 2 times 2 times 2 times 2, which is 2 to the 5th power. How about if I wrote it this way? I wrote 32 as 2 to the 4th times 2 to the 1 power. Why didn't I leave it as 2 to the 5th power? Because I want to get the exponent to match the index. So now I've got the fourth root of 2 to the fourth times the fourth root of 2 to the 1, or just 2, right? I don't really need to write that 1. Well, what's the fourth root of 2 to the fourth? It's 2 outside the radical, and left inside we have the fourth root of 2. Okay. New problem. Square root of 50x squared. Simplify each radical expression. All variables represent positive real numbers. Okay, so what they're saying now is we don't need to worry about absolute value bars in these problems. They're telling us up front, assume the variables all represent positive real numbers. Okay. So since my index is a 2, I want perfect square factors. Okay. 50 is 25 times 2. 25 is a perfect square. Okay. So this becomes the square root of 25 times the square root of 2 times the square root of x squared. What's the square root of 25? It's 5. The square root of 2 can't do anything with. What's the square root of x squared? It's x. So I'm going to put the nice stuff in front and the radical stuff at the rear. So 5x square roots of 2. All right with that? Now, I want to do the same problem again, but I want to do it with using slightly less writing, okay? From there, I went to this next step and pulled it all apart. Now I'm just going to leave it inside and I'm going to say, okay, let's deal with this. What's the square root of 25? That's a 5 outside. Can't do anything with that. The square root of x squared, that's an x outside. So I've got 5x square roots of 2. Okay, that saves me writing this step. I go straight from here down to there and then to the answer. Okay. All right. Square root of 75 b to the 8th c. 75 is 25 times 3, right? And 25 is a perfect square. I could do this. I could write this whole thing like this. I could go 25 times 3 times b squared times b squared times b squared times b squared times c. Why did I do all of that? I'm taking b to the 8th power and writing it as b squared, but there's 4 of them, right? Because b squared times b squared times b squared times b squared, you'd add up the exponents, okay? And don't freak out if you're going, oh, this is too much work. I want to start here, but I'm going to show you a better way here in a minute. Okay. So the square root of 25 is 5 on the outside. The square root of 3, that's not going anywhere. That's stuck inside. The square root of b squared is b outside. The square root of b squared is b outside. The square root of b squared is b outside. The square root of b squared is b outside. And what's left inside is what? 3c. So I've got 5b to the 4th square roots of 3c. Okay, there's my final answer. Now, let's take a look at b to the 8th power just by itself. If I'm going to take the square root of b to the 8th power, I'm going to go ahead and write that index, the implied 2. That's b to the 8 divided by 2, which is b to the 4th power, right? The square root of b squared is b. What's the square root of b to the 4th? Wouldn't that be b to the 4 halves, or 2? And the square root of b cubed, whoops, slow down. The square root of b to the 6th would be b cubed. The square root of b to the 8th is b to the 4th. What's the square root of b to the 10th? That would be b to the 5th. So if this exponent matches the index, they undo each other. They reduce down to an exponent of 1. But what if this is a multiple of the index? it still comes out nicely. So going back to this problem, let's do it a second time, okay? And here's what I'm gonna do. All right, 75 is 25 times 3. B to the 8th, 8 is a multiple of the index. So I'm gonna just leave it like it is, okay? Now, the square root of 25 is 5 on the outside. The square root of 3 doesn't go anywhere. The square root of b to the 8th is b to the, what's 8 divided by 2? 4. And the c doesn't go anywhere. So I get that. So that's kind of the streamlined process of what I did way back up here. Okay. All right, take a look at this example.
Good question.
Yes.
Going back on that one, I'm a little bit confused. So how do you know which one goes outside and which one goes inside?
Okay, let's just take this for instance, okay? Just that part, the 75. So I could write that as 25 times 3 inside, okay? You all right with that?
Yes.
Is that a perfect square?
No. Yeah.
5 times 5. So yes, it is. So I'm going to take the square root of 25, which means the 5 now goes outside because I took the square root. But the square root of 3, I can't do anything with.
Oh, okay. Got it.
So yeah, so like here, that went outside as this, that went outside as that, but these didn't contain any perfect squares, so they're stuck inside.
Okay, now I get it.
All right, excellent, excellent. Let's see here. How about this? The cube root of 280, a to the 5th, b to the 6th. All right, so the index is a 3. I want exponents inside that are either 3s or multiples of 3. Okay, let's start with the 280. 280 is 28 times 10, 2 times 14 times 2 times 5, 2 times 2 times 7 times 2 times 5, 2 cubed times 5 times 7. Now, what did I just do? I just did the prime factorization of 280. I broke it down into its smallest factors that are primes, and I put the like factors together to get powers, okay? Oh, that's a cube. So I've got the cube root of 2 cubed times 5 times 7. Now, a to the 5th power, I'm going to write as a cubed times leftovers. A cubed times a squared. Why am I going to do that? Because a to the cubed, I can take the cube root and get it outside. A to the 5th power, I can't do that. But if I pull out this much and then leave that left over, I can still undo that first a cubed. Now, what about b to the 6th? B to the 6th, 6 is a multiple of the index, so that's going to come out nicely. So all my exponents are either 3s, multiples of 3s, or they're not either one. The stuff that's not either one is going to be inside at the end. Okay? So here we go. The cube root of 2 cubed is 2 on the outside. The cube root of 5 is stuck inside. The cube root of 7 is stuck inside. The cube root of a cubed is a on the outside. The cube root of a squared is stuck inside. The cube root of b to the 6th is b squared, right? Because 6 divided by 3 is 2. Now, what's left inside? I've got 5 times 7 times a squared. So my final answer, I'm going to go ahead and multiply back together the stuff inside and write it like that. So I pulled it apart into powers that were cubes or multiples of cubes and leftovers. I pulled out all the cubes and the multiples of cubes by taking the cube roots and the leftovers were stuck inside at the end. The idea is to kick things out that match the index to reduce things down. So you want to do all you can to get things to match the index for the exponents inside. All right. Now, another rule that takes us back to chapter 5, if we have a quotient raised to a power, we apply the power to both the numerator and the denominator of the quotient. And we've looked at this earlier today. But what if I had a over b to the 1 over n power? That would be a to the 1 over n over b to the 1 over n power. What if I wrote this in radical notation? This would be the nth root of a over b equals the nth root of a over the nth root of b. So what does that mean? That means if we've got a fraction inside of a radical, we can separate the numerator and the denominator into different radicals, but with the same index. We actually did some problems like this in yesterday's homework, but I didn't officially talk about that. Yes, that this is legal to split it up that way. Okay, now, how does that come into play? Let's say we've got the following situation. It says simplify each radical expression. All variables represent positive real numbers. We don't have any variables here, but this would be the square root of 3 over the square root of 4. The square root of 4 is 2. So I could simplify the denominator. I can't simplify the numerator. Okay. Questions on that one? How about this? The fifth root of 2 over 243. So that's equal to the fifth root of 2 over the fifth root of 243. Well, 243 is 3 times 81, which is 3 times 9 times 9, which is 3 times 3 times 3 times 3 times 3, which is 3 to the 5th power. So I've got that. So 243 is 3 to the 5th power. Well, what's the 5th root of 3 to the 5th power? The index and the base reduce each other out, and you've just got a 3 in the denominator. So it's the 5th root of 2 divided by 3. How many of you feel like I'm just speaking a foreign language today? Wah, 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 wah. Yeah, like Charlie Brown. Yeah. Okay. How about this one? The square root of b to the 4th over 64 a to the 8th. So this would be the square root of b to the 4th over the square root of 64 a to the 8th. What's the square root of b to the 4th? That's b squared. What's the square root of 64? That's 8. And the square root of a to the 8th would be a to the 4th. So b squared over 8 a to the 4th. Now, not only can you split them up, you can also put them back together. So let's say I've got this, the square root of 500 over the square root of 5. Since they have the same index, I can write that as a single fraction inside the radical. But in this case, I can then reduce it because 500 divided by 5 is 100, and the square root of 100 is 10. I thought that was pretty cool. I'm probably the only one, but still. All right, what about this one? The square root of 128 over the square root of 2. That would be the square root of 128 over 2, which is the square root of 64, which is 8. So again, here we were pulling things apart. Here we're shoving things together. Okay, what about this one? The square root of 75 y to the 5th over the square root of 3y. So that would be the square root of 75 y to the 5th over 3y, all inside the same radical. but 75 over 3 is 25, and y to the 5th divided by y to the 1 is y to the 4th power, and that would be 5y squared outside. Have you ever heard somebody say, I wouldn't want to be a member of a club that would want to have me as a member? It's kind of like a self-insult sort of thing. Well, the club here is the index club, and the idea is to get kicked out of the club, okay? If the index is a 2, you want to find all the squares and kick them out. If it's a 3, you want to find all the cubes and kick them out, okay? So the index is the key to this whole thing. All right, how about this one? The cube root of 243x to the 8th over the cube root of 9x. So that would be the cube root of 243x to the 8th over 9x. All right. Well, let's see. Does 243 divide by 9 evenly? 243 divided by 9. Yes, 27. So this would be the cube root of 27 x to the what, 7th? Okay. X to the 8th divided by x would be x to the 7th. But I could write that as the cube root of 27 times x to the 6th times x to the 1. Now, why did I do that? 27 is a cube, 3 times 3 times 3. X to the 7th, 3 doesn't go into that evenly. But if I pull it apart as x to the 6th times x to the 1, the cube root of 27 is 3. The cube root of x to the 6th is x squared, and I've still got an x left inside. Okay. We're getting ready for the final approach to the runway. This says simplify by combining like radicals. What's 2x plus 3x? That's 5x, right? What would 2 square roots of 5 plus 3 square roots of 5 be? That would be 5 square roots of 5. What would 3 square roots of 17 plus 10 square roots of 17 be? That would be 13 square roots of 17. Do you see how I'm getting at these like radicals? This isn't actually like radicals, but that's just the familiar. So here, they're both something times the square root of 5, so I add together the somethings. Okay, are you good with this? Well, we'll find out. Okay, 11 square roots of 3 plus 2 square roots of 3 would be 13. Whoops, messed that up. 13 square roots of 3, right? Adding like radicals. Okay, 30 cube roots of 6 minus 10 cube roots of 6 would be 20 cube roots of 6. In this case, subtracting like radicals. All right, now what if we got this scenario though? 9 plus the square root of 45. 9 plus the square root of 45 plus the square root of 20 plus 16. Simplify by combining like radicals. Well, 9 and 16, those are just whole numbers. Those can go together. But the square root of 45 and the square root of 20 don't look at all alike. The key to this problem is to simplify each radical term first. Okay, so what have we got? We've got 9 plus, let's see, 45 is 9 times 5, and 20 is 4 times 5. So by doing this, I can now come back and say, well, this is 9 plus the 3 square roots of 5, because the square root of 9 is 3 outside, plus 2 square roots of 5, because 4 as a factor inside. Take the square root, you get a 2 outside, plus 16. Oh, look, now those are like radicals, and these are like constants. 25 plus 5 square roots of 5. So simplify each radical and then combine the ones that are alike. Let's take a look at another one. square root of 20 plus the square root of 125 minus the square root of 80. Okay, so 20 could be written as 4 times 5. 125 could be written as 25 times 3. And 80 could be written as 16 times 5. Now, for the sake of time, I went right to the perfect square factors. But let's say you can't just look at 80 and see that it's 16 times 5. It's like, oh, I wouldn't have caught that perfect square. So the long way is to break it down. So there's 2 to the 4th power. That's a perfect square, right? Because the exponent's a multiple of 2. So if you can't just see it, break it down and then build it back up. So now what have I got? Well, this is going to be 2 square roots of 5 plus 5 square roots of 3 minus 4 square roots of 5. Oh, they don't all go together, do they? You know what? I messed up. My multiplication messed up right there. What should that have been? Should have been a 5. Yeah. So then I would have had that. Sorry about that. In my haste to try and finish on time, that's always a bad thing when I do that. So 125 is 25 times 5, not 25 times 3. That would have been 75. Now, all 3 of them are alike, aren't they? So 2 of something plus 5 of something is 7 of something. 7 of something minus 4 of something is 3 of something. Okay? One more example. (23) 4th roots of 3 plus the 4th root of 48. Well, 48 is 2 times 24, which is 2 times 2 times 12, which is 2 times 2 times 2 times 6, 2 times 2 times 2 times 2 times 3, 2 to the 4th times 3. Okay? So I've got 23 4th roots of 3 plus, what's the 4th root of 2 to the 4th power? That's a 2 outside. Oh, 23 4th roots of 3 plus 2 4th roots of 3 is 25 4th roots of 3. So simplify each radical and then combine the ones that you can. All righty. Well, that's it for today. This is Thursday. So Monday, we're going to do, what is it, 9.5, I think it is, and chapter review. And then Tuesday is our next test. So over the weekend, you've got 9.2 and 9.3 to finish. I will be back on Monday with an office hour. Hardly anybody ever comes to the office hour, so I would really encourage you, if you've got a lot of questions, if you can get here before the 11 o'clock hour, go to the office hour Zoom meeting between 10 and 11. And otherwise, I will see you all later, and Jamie will stick around for a minute and make sure you're okay with your calculator stuff. But I'm going to stop it, so have a good weekend.